Have you ever wondered how calculators do integration? Well, definitely not like us by using the Newton-Leibniz formula, because most graphic calculators, like the Casio FX CG50, cannot compute antiderivatives. They use instead numeric integration.
In other words, they approximate the end result of the integral. They don't calculate it.
That's not unfamiliar, is it? We've covered several approximation techniques this year, namely the Riemann sum, which uses rectangles, and the trapezoid sum, which uses trapezoids.
But these are very bulky methods. They use straight lines to approximate a smooth function. I mean, it's gotta give some inaccuracies, right? Well, that is the exact thing we're looking at today, another way of approximating polynomials that's more accurate and more smooth. Ladies and gentlemen, may I present to you the Simpson's rule.
Now, what is the Simpson's rule?
Let there be some y equals fx on the closed interval ab. We then take the two endpoints and the midpoint on this interval. Using these 3 points, we make a quadratic function, and if you look closely, these two graphs match together quite well.
And since a definite integral is basically the area underneath the curve, to get the definite integral here, we calculate the area underneath the parabola instead. And with a little bit of algebraic simplification, we get this formula. And for the interval from a to b with an even number of subintervals, the composite Simpson's rule could be used to even closer approximate the results.
So, in summary, although the Simpson's rule is able to give a closer approximation to the smooth function, its calculation complexity is considerably higher as well.
Amazing. Now, to know this rule more in depth, we have to dive deeper into its history. The Simpson's rule was invented by 18th century British mathematician Thomas Simpson.
Not quite. My man didn't invent the rule, someone else did. The core concept of using quadratic approximations for numerical integration was first developed by the Scottish mathematician James Gregory in the 1660s. Gregory derived a general formula for numerical integration using polynomials of arbitrary degree, and quadratic functions were a special case, which evolved into the Simpson's rule in the next century.
Though, unfortunately for Gregory, his work was not widely accepted and used during his lifetime, and the method remained obscure until Simpson popularized it in his 1740 textbook, A New Treatise of Flux Ions. And this is how the rule became Simpson's instead of Gregory's.
The Simpson's rule is such a great tool back then, and even now, before the advent of calculators. Most mathematics were done by hand, and tricky polynomial integrations were almost impossible. The Riemann sum is one of the methods to conquer them, but it is too inaccurate for some very curvy polynomials. The Simpson's rule came along and solved this problem perfectly. So thanks a lot to Mr. Thomas Simpson then.
Alright, we have said in the past that the Simpson's rule might be more complicated than the Riemann sum or the trapezoidal sum. But how complicated is complicated? We designed an experiment to find out.
Us three will receive the same integral, and I'll use the Riemann sum.
And I'll use the Simpson's rule.
I'll use the trapezoidal sum.
They will each approximate this integral and evaluate it using their respective methods, and I will time them. At the end, I will note their time and correct them. And we have some results. The Riemann sum finished first, as expected, followed by the trapezoidal sum, and finally the Simpson's rule. As you could see these results shown on screen, the Simpson's rule is by far the most complicated method of approximating an integral among all three. But, as earlier said, this method also yields the most accurate results. So, life always have trade-offs, and this is no exception. And now we have addressed all major issues this video is about. Let us wrap up with some conclusions.
The Riemann sum has the lowest calculation complexity, is easy to learn and apply, and works fine for discontinuous functions as well. This marks it as an ideal method for introductory calculus, such as AP Calculus BC.
The trapezoidal sum is somewhere in the middle. It is a bit more complicated than the Riemann sum and a little bit more accurate because it used slanted lines to approximate. It is a reliable choice when speed is required as well as accuracy.
The Simpson's rule is the king of all. It has the highest accuracy rate, but the slowest calculation time. Calculators especially favor this method because they can calculate fast by nature. As for manual calculations, this method is best when you need accuracy but you don't want to use Taylor's expansion.